And we are going to start part 4 of section 1.4. I need to look at my schedule here. This is the last part. So tomorrow we'll get into section 1.5 a little bit. We are going to be doing a lot of graphing on our calculators today. So hopefully that you've got one. I am missing a calculator, by the way, just letting you know if anybody accidentally walked off with it. It's in your locker. No big deal. Not judging. I know you turned yours back in. You're good. But I would love to have that back. That way, we have everything back together again. So just let you know, no judgment if you need to bring that back in. Let me go ahead and put the directions up here. And I think the directions changed a few times today. So this says, discuss the continuity of the function on the closed interval. Discuss the continuity of the function on the closed interval. So what we're doing today is, when we look at continuity, we're not going to be looking at the entire function. It is going to tell us specifically what interval to look at. So the interval will be x values, and that's the only chunk of the graph that you are concerned about. Everything else doesn't matter. You're just looking at the closed interval. Okay, so this is example 1. You have your function f of x equals square root of 25 minus x squared. And the closed interval is from -5 to 5. Let me first remind you what a closed interval means. The closed interval means, and again, these are x values right here, but it means you can equal -5, you can equal +5, or you can be anything in between. But closed, the brackets there, it means you can equal those x's. So what I'm going to do is, I'm going to graph that function on my calculator, and you can do this with me, and I'm only going to be looking from -5 to +5. Okay, so I'm going to go ahead and pull mine up here. It was square root of 25 minus x squared. I'll go ahead and graph that. Okay, well, actually, our interval was -5 to +5, and for this function, that's pretty much what the domain is anyway. It doesn't even go past -5 and +5. Now, if you are a little concerned about these end points right here, remember, for continuity, you can't have holes or anything. So, my calculator, I'm not really sure if it's coming down right on the x-axis or not, but you can trace to -5 and it gives you back a y, or you can trace to +5 and it gives you back a y. So there's really nothing that I'm concerned about here. I don't care that nothing is going on out past these x values, because my closed interval was just -5 to +5. And it's all looking continuous to me. So what I would say is, it is continuous on, and I wouldn't say continuous everywhere, because it doesn't really exist everywhere. We need to just say continuous on the interval, the closed interval, -5 to 5. All right, you're only looking at those x values that they give you inside the interval. Let me keep going here. We'll get to some that are a little bit different. Number 2 says f of x equals 2 over x squared minus 9. 2 over x squared minus 9. Now, on that interval, I'm just looking at -1 to +3. Those are the only x's that I'm concerned about. Now, actually, before I jump to my calculator, if you look at this function and you think about your domain killers, what x's should we be concerned about? 3 and -3. Now, really, with this interval, since it starts at -1, I guess I'm not really concerned about -3 because it's not even on the interval, but 3 is. So knowing that ahead of time, I know what to look for on my graph. I am most concerned about where x is 3. So let me go ahead and graph this first, and then we'll look at it. You do need to put the denominator in parentheses, x squared minus 9. So again, you're not looking at the whole thing. You're just looking from the x value of -1, which is right there, to the x value of 3. I'm going to go ahead and put a line here, but it appears that there's a vertical asymptote where x is 3. Everything else in this interval is fine. Remember, I'm not concerned about -3 because it wasn't even in the interval. Everything else over here is fine except for where x is 3. Now, to discuss that or to describe that back on the problem, I'm going to put a couple different things that you could say. You could say that we're continuous on the interval -1 to 3, but you would have to change the 3 to have parentheses because you can't really equal the 3. There's a vertical asymptote there. That would be fine. That would be an okay answer. Another thing you could do is kind of describe like what the discontinuity is. You could also say that there's a non-removable, because the limit did not exist there, non-removable discontinuity at x equals 3. That would also be fine. We're not really going through all of the conditions, but I guess that's another way you could say it. Those conditions, though, kind of go along with the removable, non-removable stuff. So again, either one of those answers would be fine. Okey-doke. Any questions about those? Just looking at specific intervals. Let's keep going here, and I'm going to change the directions for the next problem, or problems. I think there's 2 of them. Now it says, discuss the continuity of the composite function h of x equals f of g of x. Discuss the continuity of the composite function h of x equals f of g of x. F of g of x is fog, by the way. That was our composite functions that we learned back in probably Algebra 2. But here is our functions for number 3. It says f of x equals 1 over x, and then g of x equals the square root of x minus 1. It's not giving you a specific interval to look at, so we are going to have to kind of look at the entire function, but the function that we're supposed to be discussing is h of x. So let me do a little bit of work right here to actually figure out what h of x is. So it tells me up there in the directions, h of x is f of g of x. If you forgot how composite functions work, this means I have to take g of x, plug it into f of x. So take g of x, plug it into f of x. Wherever you see x right here, replace it with the square root of x minus 1. This is the function that we're going to graph. Now, just by looking, what is the x value that we should be concerned about? 1. An x value of 1 would make the bottom equal 0. So I like to go through that ahead of time just so I know what to look for on my graph. Okay, and again, I'm graphing, what was it? 1 divided by, since you're setting up a square root on bottom, the square root is going to keep everything together and you don't really have to have parentheses there. So there's that, 1 over square root of x minus 1. I know that x cannot equal 1. Well, this is where x is 1. And again, calculators are kind of deceiving. On mine, it looks like it stops right here where y is 4, but I'm pretty sure that's going to just keep on going up right next to the vertical asymptote. So to discuss this continuity, I would maybe kind of go back to an interval type of deal, just because of that vertical asymptote. Nothing even exists over here. So one way to discuss the continuity is to say continuous on, I'm going to set up an interval here. I'll start with the x value of 1, but I would have to have parentheses there just because you can't equal 1 since there's a vertical asymptote, and it would be continuous all the way through all the rest of those x's. So that would end up being 1 to infinity. Remember, with infinity, we always use parentheses. Negative infinity, you'd use parentheses too. So that's just describing the interval on which it's continuous. You could maybe also say something about the type of discontinuity. Since, you know, the limit doesn't really exist where x is 1, I guess we could say non-removable. But on something like that, I kind of like to just set up the interval because it doesn't really exist everywhere anyway. Okey-doke. I'm going to try one more like this. Stop me if you have any questions. Number 4, f of x equals cosine of x and g of x equals x squared. Well, we need to find the continuity of h of x, which again is fog, f of g of x. So let's take g of x, plug it in to f of x. So wherever you see x over there, replace it with x squared. Okay, now I'm not really seeing any domain killers that make me nervous. Trig functions are a little bit different anyway, so I may just go ahead and graph this one to see from there if there's any kind of discontinuities. So I'm graphing cosine of x squared. Let's see here, and I think we talked about this the other day. It may actually matter that you're in radian mode, so double check that. You probably don't have to in parentheses since there's nothing else to type in. But there you go, looking a little crazy. Oh, okay, slows down in the middle, but it is a cosine curve. It kind of looks like a heartbeat or something, but it is a cosine curve. There's no vertical asymptotes, no breaks in the graph or anything like that. So I would say continuous everywhere. If you wanted to stick with the intervals, you could say continuous on negative infinity to positive infinity. But if you said continuous everywhere, that would be fine too. It didn't really say in the directions that we had to state the interval, so it would work either way. Alrighty, any questions about those? I think I've just got one more type of problem here. So, directions. Now, they actually tell me specifically to describe the intervals. We're going to do 2 of these. Describe the intervals. I'm going to underline intervals because you have to use intervals here, on which the function is continuous. Describe the intervals on which the function is continuous. So if it's another one that's continuous everywhere, you would not be able to just say continuous everywhere. You do have to have an interval. So it would be negative infinity to positive. Okie doke. Here is number 5. F of x equals the square root of x minus 3. Square root of x minus 3. Well, I don't really know what this is looking like until I graph it. So that's kind of the main deal today. We're going to have to graph each one to take a look. I am worried about one of my domain killers, which is that you can't take the square root of a negative. So that may have an effect here on what we say, but let's just see what happens. Square root of x minus 3. I mean, it's a square root graph shifted right 3. I probably could have graphed that without my calculator. So, I mean, it's not continuous for any of these x values because it doesn't even exist over here. It starts existing where x is 3. And if you want to just check that there's actually a point there, not a hole, you do get back a y value of 0. So I would say for this one that it's continuous on, I'm going to set up my interval now. It starts where x is 3 and it can equal 3 because we just saw there is a point there, and it'll be continuous for everything else past 3. So that would have to be our answer here. We have to say it in intervals. Continuous on the interval 3 to infinity. Okie doke. Kind of the same thing going on with each one today. Let's go ahead and finish with number 6. Pretty short lesson. F of x equals x over x squared minus 4. Just by looking at the function, what x's should we be concerned about? Yes, 2 and negative 2. I am going to graph this, but I know ahead of time what x's to look for. So, last one, we have x divided by parentheses x squared minus 4. I'll go ahead and graph that. Okay, remember you have to use intervals. You can't just say what type of discontinuity. You have to say an interval. So let me go ahead and just kind of set this up down here. There we go. Continuous on. I'm just going to start on the left and work my way to the right. I'm starting at negative infinity, because that would be all the way to the left here. And I'm continuous all the way until I get to where x is negative 2. Now, can we equal negative 2? No. So parentheses. Now, I am going to have to do a couple more intervals. So let's go back to that union notation that we sometimes use. And now I'm working with the part in the middle. This part goes from negative 2 to positive 2, but it can't equal either one. So I've got parentheses with both of those. And then finally, last interval starts where x is 2 but can't equal 2. It's just really close to it. And it will go all the way to infinity. So we've got a long answer right there on number 6. But again, anytime you have to use an interval, best way to do it is graph. You know what to look for ahead of time, but calculators make that a little bit easier. Any questions about those? Very good. This should be our assignment here. This is C24 from pages 96 to 97. We're all over the place. 33 to 36, 69 to 72, 77 to 79. I think the last few are the ones where you have to use intervals. All the rest of them you can possibly describe those other ways.